Hello, welcome to episode 3 of Maths in an Empty Classroom with me, Mr. Southern. We're going to look now at example 3 of connected particles on an inclined plane. If you're wondering what happened to example 2, you are able to access this on the Ringwood School Learning Zone. I didn't go through it because there's a full worked example up there and it's basically the same as example 1 with the numbers changed. So I thought let's crack straight on to look at example 3. So here we have particle A of mass m kilograms. So straight away you can see m kilograms, we haven't been given the mass. Rests on a rough inclined plane making an angle theta to the horizontal where sine theta equals 3 over 5. We'll talk in a minute about how to deal with that. The coefficient of friction between A and the plane is 1/4. A is connected to a particle B of mass 2m by a light inextensible string which lies along a line of greatest slope of the plane and passes over a smooth fixed pulley at the top of the plane. B is hanging freely 1 metre above the horizontal plane and A is initially 2 metres from the pulley. So similar scenario to what we always have, with a bit of extra information and some more things that at this stage are unknown. So as we always do with mechanics, we start off by drawing a nice big diagram and labelling everything we know about the system. So here is our inclined plane. Let's just modify that so we can actually get the pulley into it. There we go. And we have the angle theta, because we didn't know the angle at this stage. We have a particle A just place there. We've got the smooth fixed pulley at the top of the plane connected by the light inextensible string. And then we have the particle B hanging freely. Now we were told that particle A had a mass of m kilograms, particle B had a mass of 2m kilograms, and we were also told that initially particle A is 2 metres from the pulley itself. So I'm just going to draw on there a line that is 2 metres away from the pulley. Right, let's just have a little look back at it. Right, so particle A of mass m kilograms rests on a rough inclined plane making an angle theta to the horizontal where sine theta equals 3/5. The coefficient of friction between A and the plane is 1/4. Right, so let's just deal with a couple of those things then. We've got that the coefficient of friction is 1/4, so I'll write that over there. And we've also got that sine theta equals 3 over 5. Now what you don't want to do with that information is inverse sine find theta, because it's not really a very nice number, and it will just mean you've got more and more decimals to deal with in your calculations. What you need to do instead is to find the exact value of cos theta, because that's what we're going to use in our calculations. And the way to do that is just to draw out a very quick triangle, right angle triangle with an angle of theta. Now if sine theta is 3 over 5 and sine is opposite over hypotenuse, it means you have an opposite of 3 and a hypotenuse of 5, which using Pythagoras means that your adjacent must be 4, and therefore cos theta using adjacent over hypotenuse must equal 4/5. If you do enough mechanics, that's the kind of thing that you will just be able to see and remember rather than having to draw out that triangle every single time. Okay. Right, quick glance back at the question. A is connected to a particle B of mass 2m kilograms by a light inextensible string. We've done all that. B is hanging freely 1 metre above a horizontal plane and A is initially 2 metres from the pulley. So let's get that onto our diagram, the fact that B is 1 metre above the ground initially. And then what we need to find out is what way is the system moving, because as I mentioned before, that is going to determine the direction of friction, which is very, very important. So when the system is released from rest with the string taut, A moves up the plane. Right. So A moves up the plane. So let's get our acceleration arrows on here for A moving up the plane. And if A is moving up the plane, that means that B must be moving down the plane. So we'll label that on here. So I've now got the initial diagram set up. What I'm going to do now is label all the forces that are acting on this system. Starting with the weight of A acting straight down. Now I don't know the mass of A other than it's M, so I just have to label this as mg, where m at this stage is the unknown mass. Now remember, this weight is acting in a direction that isn't parallel or perpendicular to the plane that A is on. So I'm going to draw my dashed line in perpendicular to the plane that A is on, because I know that doing that creates the same angle theta here as I've got here. And while I'm there, I'm going to resolve that weight into its parallel and perpendicular components, because the weight down the slope is the bit that people always forget to do. So perpendicular to the slope, I have mg cos theta, and parallel to the slope, acting down the plane, mg sine theta. And these are the components of the weight of A. We also have a reaction force acting on A perpendicular to the slope. We have a tension force that is acting on A to pull it up the slope. We have an equal and opposite tension in the pulley, in the string I should say, sorry, acting on the pulley downwards like so. And because we now know that A is moving up the plane, friction will be opposing the direction of motion, so friction will be acting down the plane. I can draw that on in that direction, and they are all the forces acting on particle A. So now let's look at the forces acting on particle B. We've got its weight directly downwards, which is mass times gravity, so 2 mg. We have a tension force in the string acting on B going upwards, and we have the same tension force acting on the pulley going downwards. And as mentioned before, all four of these tensions are the same magnitude, same value, same number. Okay. Right, so let's now have a look at what we're being asked to do in the question. It's asked for the initial acceleration of A. So what we're used to doing by now, let's wait for it to respond. There we go. Right, so part A. I'm after the initial acceleration. As always, I begin by resolving perpendicular to the plane. So resolve perpendicular to the plane. And what I have going on here, again, I'll get my ruler like I did before, anything acting perpendicular to the plane. And I've got those two forces there. I've got normal reaction force, and I've got mg cos theta, which is the perpendicular component of the weight of A. And I know that those two things must be equal, because A is sliding along the plane, it's not moving up or down. So mg cos theta. Now at this stage I know that cos theta is 4/5, because I worked that out earlier. So what I'm actually going to write is that the reaction force is 4/5 mg. You could write 0.8 mg if decimals are your preference. The purpose of doing that was to find out friction. So using the fact that friction is mu times R. Friction is 1/4, which is our coefficient of friction that we were told in the question, times by 4/5 mg, which works out rather beautifully to be 1/5 mg. So that is the frictional force acting on A. Now we've done that, we're going to resolve parallel to the plane. Using that resultant force is mass times acceleration. Resolving in the direction of motion, which is upwards. Look in here, any forces acting parallel to the plane on A I'm going to consider. So T is pulling it up, friction is pulling it back, and look, that weight component down the slope that everyone always forgets, mg sine theta. So my resultant force equation for particle A, T minus friction minus mg sine theta equals mass times acceleration. Now I know quite a lot of this as values in terms of m and g, so I can put that into it now. I know that friction is 1/5 mg, so I'm going to put that in. I also know that sine theta is 3/5 because I was told it in the question, so I'm not going to write mg sine theta, I'm going to write 3